In this lesson, we're going to look at standard deviation. Standard deviation is a measure of the dispersion or scatter of data values in relation to the mean. A low standard deviation indicates that most of the data values are close to the mean, and a high standard deviation indicates that most of the data values are scattered farther from the mean. To find the standard deviation by hand is extremely time-consuming but possible. So in example 1, I'm going to show you where this is coming from. We're going to go through and find the standard deviation of this list of data by hand. It is one of the values when we do our single variable statistics in our graphing calculator. It is one of the values that will come up, the standard deviation, and we will be using that in class, but it's important that you know where this is coming from. Now, the first step is to find the mean. Now the mean, we know, is when we add up all the values and divide by how many we have. So the mean, symbolically, would be the sum of x, so that's a summation symbol, divided by n, and n represents the number of values we have. So if I add 86 plus 91 and so on all the way to 88, if I add all those up, I get 900. You can go ahead and try that. And then how many values do we have here? Well, we have 10 of them. So the mean of this data set is 90. Now we need the mean because if we're going to find how far all of our values are away from the mean, we need to get the mean first. So B says find the difference between each score and the mean. So you can see here in the column, it'd be x minus the mean. So 86 minus 90, 91 minus 90, and so on. So we'll do that here. And then just write out your answer. So that would be -4. And the next one, 91 minus 90. And that would be 1, and so on. So take a minute and go through and find out what this column is equal to, okay? Once you get all the answers for that column, the next step is to square each of the differences, and that's in column 2. So we take our answer for x minus x bar, or the value minus the mean, and we square that. So for example, we would have -4 squared. And that would be 16. 1 squared would be 1. Don't forget to use brackets when it's negative. You can use brackets for all of them. -1 squared, which would be +1, and so on. So go ahead and do that next. At this point, we've done quite a bit of work, but we're still not done. So you can see we've only got 10 data points here, and already finding the standard deviation is quite tedious. So the final step that you have to do is to use the information that we just figured out and calculate the standard deviation using this formula. So this sigma here, that's the symbol that represents our standard deviation. So it's the sum of x minus the mean squared, all divided by n. So let's substitute everything we've just figured out. So we're going to add the sum of x minus x squared, which means take everything in this column and add them up. So 16 plus 1 plus 1 plus 4. And when you do that and add them all up, the sum of x minus the mean squared gives us 36. And you can double check that I did that right. So 36. So that's what they're asking us to do in the top part here. So sigma is equal to 36 divided by n. We've got 10 values here, and the whole thing, top and bottom, is all square rooted. Okay? Plug that into your calculator and you get the standard deviation is 1.898. What does that mean? Right? Like, we've done all this work, but what does that mean? That means, right, if we go back to the definition at the top, how far, a measure of dispersion of, or scatter of the data values, how close the values are to the mean. And it says a low standard deviation indicates that most of the values are close to the mean. High standard deviation indicates that most of the data is scattered farther. Now if our mean is 90 and you look at our values, 86, 91, 89, all of those are actually pretty close to 90. 86 is the furthest away. But most of our values in this list, so if we look at 1.898, that's actually not too bad in terms of a standard deviation. But it's all relative to the data that you have, right? Because our value is 90, so you know, just over 2 away from the mean isn't too bad, but it depends on what we're measuring. Let's go ahead and see how to calculate this by hand, and then see what kind of meaning the standard deviation has in a couple different situations. Let's take a look at the next example. Up here we've got the information on how to find the standard deviation in your graphing calculators. So that means we're going to be putting in data, and then we're going to look at the list. So we'll go through that together. Now it says try example 1 using the calculator and compare. Let's go ahead and do that. So I've gone ahead and put in all of my data into list 1. Now it's nice to do this with the calculator for the first time with data that we've already know the answer to, just to make sure that we're doing this right. So it says enter data into stat in list 1 and possibly list 2 if a frequency table is used, but this isn't the case. Then it says press stat and arrow over to calc. So this is the same thing we've been doing. Oops. And then, okay, we're going to be doing single variable statistics once again. So go into there, enter, and here we go. So if you arrow down, you can see the value we're looking for is the sigma x right in here. So 1.8973 and so on. So if we write that down here, 1.8974, I guess, that's sigma x equals 1.8974. If we compare that to what we had before, by hand we had 1.898. So you can see that those values are quite close to one another. One's just doing it a little bit differently in the calculator. So that's what we're going to be doing, okay? We're going to be using this method in our calculator, because otherwise it's going to take us so long to figure out the standard deviation. If we have a tool that we can use to get there, then that's what we're going to do. Okay, so let's try example 2. Brendan works part-time in the canteen at his local community center. One of his tasks is to unload delivery trucks. He wondered about the accuracy of the mass measurements given on 2 cartons that contained sunflower seeds. He decided to measure the masses of the 20 bags in the 2 cartons. One carton contained 227 gram bags, and the other carton contained 454 gram bags. So you can see here from the data, we've got 2 sets, okay? We can put this set into L1. We could put this set into L2. Now, it's not a frequency table. We're not measuring them against each other. We're just putting both sets of data in. So the 20 bags that measure 227 grams and the 20 bags that measure 454 gram bags. Now it says, how can measures of dispersion be used to determine the accuracy of measurements is the same in both bags? So before we do that, let's go ahead and figure out what the range, the mean, and the standard deviation is for each bag. So let's put our data into our graphing calculator. I'm going to make this bigger here. So we're going to go back into stat 1. I'm going to clear this out, and I'm going to go ahead and put all the data from the 227 gram bags into list 1 and all the data from the 454 grams into list 2. Once you have all your data in, let's go to Stat, Calc, 1 variable statistics, and we're going to do this on L1 first. So here I can see my mean is 227.15. I can see my range by getting my minimum and maximum values here. Min is 218, and my max is 236. And then I can see my standard deviation was up here as well at 5.22757 and so on. So let's go ahead and record this data in our notes. Okay, so I'm going to create a bit of a table here. So I've got the bag size that we're looking at, and then I'm going to do the range, the mean, and then the standard deviation. And I'm just going to use the sigma symbol. Once we have all our data, then we can compare it. So we've got the 227 gram bag, that was what I just calculated in list 1, and we've got the 454 gram bag. So the range we said was 236 minus 218, which gives us a range of 18 grams. The mean, 227.15 grams, and their standard deviation, 5.227 grams. Okay, go ahead and do the same thing with the 454 gram bag. So we're going to go stat calc, one variable statistics, but now we're going to do that on L2, enter. And here we've got our mean is 454.4. We've got our standard deviation, 4.49888, and so on. And we can get our minimum, 445, and our maximum down here is 436. Okay, so let's record that. The range, 400, did I say 36? 63, sorry. 463 minus 445. And we've got 18 grams as our range. And if you look at the range for the 227 gram bag, those are the same. The mean, 454.4 grams. And our standard deviation of 4.498 grams. I'm just doing some rounding here. Okay, so when we are looking at this data and comparing it with between the two bags, the range is actually exactly the same. So the range doesn't really tell us that much, right? If we look at our mean, well, it's supposed to be a 227 gram bag, 227.15. Okay, that's close. 454 gram bag, and we've got 454.4 grams. Again, that's close. What about standard deviation? Well, the standard deviation for the 227 gram bag is higher than the standard deviation of the 454 gram bag. Okay, so what does that mean? That means that there's a bigger range. Well, not really, because the range is the same, but the difference between the mean and the highest values and the mean and the lowest values, each individual value, not just the highest and lowest, but each individual value in this list, the difference between them and the mean is higher than the difference between these values and the mean. Okay, so we're not just looking at the highest value and the lowest value, we're not looking at the range, we're not looking at the mean, but the difference between each individual value and the mean, the measure of dispersion. Okay, let's summarize this. The accuracy is not the same for both sizes of bag. The standard deviation for the 454 gram bag is less than the standard deviation of the 227 gram bag. Therefore, the 454 gram bags have more consistent mass. They were filled with more accuracy. Let's take a look at B. How might the standard deviation be used by the company that sells the sunflower seeds for quality control in the packaging process? Well, you might want to use the standard deviation to make more accurate results and have less dispersion, which means that you want to have the values as close to what says on the bag as possible. The company might also want to establish an acceptable range of masses by adding or subtracting the standard deviation from the mean. So if our mean is 227 grams, which is what you want it to be because that's what it says on the bag, you might say, okay, well, it'll be 227 grams plus or minus 1 gram. So that is what we want as our standard deviation. Here we have plus or minus 5.27227 grams or 4.498 grams. Maybe you want to keep it smaller. Or maybe they say, well, if it's 3 grams difference above or below the mean, we're okay. So that's what this means, that you can set up an acceptable range according to what it says on the bag and the standard deviation. This is just an example. All right, let's take a look at another situation where we can use standard deviation to draw some conclusions. In example 3, we're going to determine the mean and standard deviation of group data. Angel conducted a survey to determine the number of hours per week that grade 11 males in her school play video games. She determined that the mean was 12.84 hours, with a standard deviation of 2.16 hours. Janessa conducted a similar survey of grade 11 females in her school. She organized her results in this frequency table. Compare the results of the two surveys. So gaming hours per week for grade 11 females, we've got the hours listed in a range, and then we've got the frequency. So this range, 3 to 5, it's great because we know that between 3 and 5 hours, there's 7 grade 11 students that fall in that range. But in terms of figuring out the statistics on my calculator, I can't input a range of 3 to 5. So what we're going to do instead is find the midpoint of the hours. I'm just going to add a little midpoint here, and let's put those in. So between 3 and 5 would be 4, 5 and 7 would be 6, and so on. You can see the midpoints for all of these. And that is what we're going to use to graph. So this is going to be my L1, and this is going to be my L2. So let's go ahead and put that data into our calculator. Clear everything out here. In L1, I've got 4, 6, 8, 10, 12, 14, whoops. And into L2, we've got 7, 11, 16, 19, 12, and 5. Okay. So because this is a frequency table, when I go to Stat 1, whoops, not Stat 1, Stat Calc 1, depending on the calculator you have, you'll either put L1, comma, L2, or put L1 into the first part and L2 into the frequency part. Okay, then hit Enter, and here are our statistics. So we already have the mean and the standard deviation for the males. And now we have the mean and the standard deviation for the females. So the mean is 8.94285 and so on, and the standard deviation down here, the sigma x, 2.7820 and so on. Alright, so let's analyze our data. Let's see what's going on. So they've given us the information for the grade 11 males, and we're going to compare that to the information for the grade 11 females. So the males were standard deviation of 12.84 hours, and not a standard deviation, that's our mean, right? X with a bar over it is our mean, and a standard deviation of 2.16 hours. Now because they rounded to 2 decimal places, I'm going to do the same thing for the females. So that would be 8.94 hours, that's the H, for my mean, and my standard deviation, 2.78. So what does that mean? Well, the average, the mean number of hours, males has more than females, right? On average, males spend more time playing video games than females. But if we look at our standard deviation, the standard deviation is lower for males. So there's more males playing video games close to 12.84 hours, and there's less females playing around 8.8. There's a bigger dispersion. So it's almost a 3-hour difference between the average. Summarizing our data, the standard deviation for the females is higher than the standard deviation for the males. Therefore, we conclude that the females' time is vary more from their mean of about 9 hours. We can also conclude that the males' data is more consistent, even though their mean is higher. That's it for today's lesson. Thanks for joining me.